Let's talk about bits. A bit is a 0 or 1. How exciting can a 0 and a 1 be? Well, we've kind of brushed on this in the course when we talked about the exclusive OR, and then this week when we talked about those 3 right arrows. And neither time was it really introduced in this way. So I'm trying to give you the mathematical / computer scientist view of ones and zeros so we can see why the shifting and the exclusive OR are actually useful. And they're not actually used in the way they've been shown in this class. At the very end I'll show you how they're actually used. So inside of a computer, everything is based on binary logic, which means two-state logic. And we can call that true and false, we can call it off and on, we can call it 1 and 0. It's all binary, 2 states. All integers can be expressed as a string of 1s and 0s. When we do arithmetic, we're used to using the digits 0 through 9. So that's base 10 because there are 10 digits, or decimal. Inside the computer, we use base 2, which is binary. You only have 2 digits, 0 and 1. There is another base that we throw into the mix here, which is base 16, which we also call hexadecimal, or frequently we abbreviate that to hex. And the reason why we use hex is because it's really easy to translate back and forth from binary to hex. It's relatively hard for the human being to translate between binary and decimal. So we use base 16 to avoid having long strings of 1s and 0s. Let's see what this looks like. So if you have 4 bits, that's 4 1s and 0s stacked together, you can make 16 combinations. And I've put the decimal, binary, and hexadecimal representations here to try and give you a feel for how this numbering system works. Now, in decimal and, well, less so in hex. In decimal, we don't write zeros to the left, right? We drop off zeros that appear to the left of the number. In binary, and quite frequently in hex, we tend to use the zeros to the left because we're tending to think of fixed width fields. So in decimal, we say 0 and we don't think about what 0 means except it's none. In binary, we tend to think of it meaning 4 bits that are all set to 0. And so 1 is not just written as 1 in binary, although it is in hex. It's 0001 to show that these 3 bits are, in fact, zeros. When we get to 2 decimal, and you'll notice 1, 1, 1. 1 looks the same in any number base. 2 can look different, only in binary, because you have 1 times 2 plus 0 times 1. So this is the 2's place, not the 10's place. This is not the number 10. This is the number 1, 0. In decimal and hexadecimal, we call it 2. 3, you can see the 1's place, or the 2's place has a 1 in it, so it's 2 plus 1 gives you 3. The 4's place is turned on, everything else is off, so it's decimal 4, binary 0100, hexadecimal 4. Once we get past 9, we're used to going to the 10's place, right? 1 times 10 plus 0 times 1 gives you 10. Well, in binary, of course, we've long since left recognizable numbers. This is not the number 1010. This is 1010. 1 times 8 plus 1 times 2 gives you 10. But in hex, it's a single digit A. So we use the digits 0 through F in hexadecimal. Sometimes you'll see uppercase, sometimes you'll see lowercase. It's not that important. If you look at some of the error messages you get sometimes, you'll see long strings of these hexadecimal numbers. And if you look, there's nothing higher than an F. And so that's a computer representation of a large number, even though we're used to seeing decimal representations. Okay? So once you get to all 1s, you can't go any further. You can't count any higher with 4 bits. So you stop at 15 or F or 1111. When I graduated from college, most computers used 8 bits, which is a byte, B-Y-T-E. You've seen lots about bytes. And incidentally, 4 bits is a nibble, half of a byte. And a nibble is also spelled with a Y, N-Y-B-B-L-E. How about that? But in 1 byte, you can have 256 different combinations, which is from 0 up to the number 255. With 16 bits, which were coming on board when I graduated from college, you can represent 65,536 different combinations, which is 0 through 65,535. because 0 has to count in here too. So the biggest number you can represent with 16 bits is 65,535. And we'll show an there's two ways of looking at that actually. We'll talk about that in just a moment. Today, computers use 64 bits at a time. That counts up to about 16 trillion. That's not an exact number, but it's approximately that. So you can see that computers today with 64 bits for arithmetic are much more powerful than computers when I graduated from college with 8 bits. Now let's back up again and talk about our operators. And yeah, maybe this isn't that necessary. It's just to remind you of what you've seen. Okay, and this would be the single AND, because true and true gives you true, everything else gives you false. Or, this is the single bar OR, everything gives you true except it's false or false gives you false. XOR, if they're different they give you true, if they're the same they give you false. And I say it that way because that's how we use XOR. If they're the same they give you the same thing, if they're different, if they're different they give you true, if they're the same they give you false. And like I say, we do have an example at the end to show how that works. So computers do the binary operations bitwise. So when you say 10100110, remember that's not 1010 and it's not 110. This is 10100110. Hex, this is an A, and this is a 6. Decimal, this would be 166. So 10 times 16 plus 6, 166. But it takes time to figure out decimal. Hex is real easy. So if you do 1010, 0110, and 1000, 1100, you go bitwise. 0 and 0 gives you 0. 1 and 0 gives you 0. Only if you have 1 and 1 do you get a 1. And so you can see when you AND things together, you tend to clear out the ones. And this will be important. When you OR things together, you tend to create ones, right? 0 or 0 is going to give you 0, but anything else, 1 or 0 gives you a 1, 1 or 1 gives you a 1, 0 or 1 gives you a 1, and so on. So you tend to create ones here, you tend to clear them here. With XOR, you tend to end up with about the same number of ones, interestingly enough. 0 XOR 0 gives you 0. 1 XOR 0 gives you 1 because they're different. 1 XOR 1, they're the same, so they give you 0. 0 XOR 1 gives you 1. When I say tend to, what I mean is that's kind of the pattern. It's not always going to be that case, but you can see we've got 3 ones here, there were 3 here and 4 here. It's about the same number of ones. Here we had 4 ones and 3 ones, and we end up with 5 ones. Here we had 4 ones and 3 ones, and we end up with 2 ones. So ANDs tend to get rid of ones, ORs tend to create ones, XORs tend to remain about the same. Then we also have shifting, and that means you take these bits and shift them a certain amount. Usually, if you have bits on the end, let's say you're shifting to the left and there's a 1 in the most significant position, you shift it off the end and it's lost. We actually talk about it going into the bit bucket, believe it or not. You can roll them so the 1 on the end would wrap around to the other end and show up as a 1 here, but that's not common in programming languages. I've only seen this at the very bottom computer level, assembly language as they call it. And typically, when you're, let's say if you're shifting to left, you'll fill in zeros on the left. If you're shifting to the right, you'll fill in zeros if you're shifting to the left, fill in zeros on the right. If you're shifting to the right, you fill in zeros on the left. Let's look at an example. Here we go. Okay. So typically we've used 2 arrows and 2 arrows for left because they look like they're pointing to the left, right because they're pointing to the right. And there's a subtle difference between 2 arrow right and 3 arrow right. We'll talk about that in a moment. But the very simple case, again, we've got 0, 1, 0, 0, 1, 1, 1, 0, and we're going to shift it left 2 positions. Now, I've done this in hex and decimal also. 4, E. That may not speak to you very well, so that number is also in decimal called 78. because it's 4 times 16, which is 64, plus 14, E is 14, so that gives you 78. When you shift this left, in the bits you can see exactly what happens. This bit moves over to the very left-hand edge of the number. These 3 bits here move over 1 position to the left, and we add a 0 on the right because we've shifted everything to the left. All right. When we shift again, this 1 drops into the bit bucket. Boop. And these 3 ones shift over, and so you can see where we started with 3 ones in a row, we still have the 3 ones in a row until we get them to the end, and then they start dropping off. So what this does, well, hex isn't really that intuitive to you right now, so maybe this isn't that useful. But here you can see when we shifted 78, which is 01001110, 1 position to the left, we multiplied by 2. 78 times 2 is 156. But when we shift it 1 more position, we actually get a smaller number. And the fact that they end in 56 is just a coincidence. That's not a property of shifting. But what happened is this 1 that was making this number large dropped off the end, so suddenly we have a smaller number than we had before. So shifting left is not really multiplying. It's kind of like multiplying. And in fact, if we had 16 bits, this bit would have just shifted 1 more position to the left, and it would have been worth 256. Here it's worth 64. Next one over, I'm sorry. Here it's worth 128. If we shifted it left 1 more position, it would be worth 256. So what happened is we shifted everything left. 156 times 2 gives you 312. But because we dropped off that 256, you have to subtract 256. 312 minus 256 gives you 56. Right shifting, we again see kind of the same pattern. This 1 moves over to here, and you can see our 3 ones that are together there, they move over 1 position. But when you shift them again, yeah, this 1 moves over, but this 1 got dropped off the end, and we only got left with 2 ones there. And so 78 divided by 2 is exactly 39. But 39 divided by 2 is 19 and a half. But since we dropped off that last bit, that's our half, we ended up with an integer value, 19. And, as I should point out, we shifted on zeros onto the left-hand side. Okay. Now, what about triple right? Well, I kind of fudged a little on double right. When you're doing a double right, the bits shifted on from the left depend on what the leftmost bit is. Okay. So if you have a 1 in the leftmost position and you shift everything 1 to the right, you shift on a 1. So this 1 moved over to the second position, and we shifted on a new 1 there. The reason why that is so is because if you were using 8-bit numbers, this 8th bit here indicates whether the number is positive or negative. So if you interpreted this as a decimal number, this is not part of the number, it just shows plus or minus. So it's a negative 0. Negative 0? Well, actually, I think you would say negative 128. That may be wrong. No, that is a negative 128, because there's no need for negative 0. But this number would be negative 56. Because this just means negative, not negative 56, negative 64, because this, come on reading, you can do this. This is the 128 position, this is the 64 position, negative 64. So the negative sign is here, and then this is the negative 64. It may be negative 65, I can't remember for sure. Negative numbers are very confusing, very confusing. So shifting right with the double arrow preserves the sign. If you shift a negative number right, it's still going to be negative after the shift. Triple arrow right is an unsigned shift, so you always shift on zeros. So even though this is a negative number, when you shift it right, so it's 0, 1, 0, 0, and I didn't show that here, I should have done that, 0, 0, 0, 0, it's now a positive number, positive 64. So they call it an unsigned shift because it doesn't care about the negative sign there. or the sign bit, I should say. Okay, so now we'll finally get down to how are these actually used. Well, in the text, the triple right was used as an integer divide. But every one of you, when you read that, you said, huh? It's not intuitive. It's not obvious. If you'd said math.floor of n over 2, that's more clear. You can work through this. Okay, I'm going to divide my number by 2, and then I'm going to go down to the next lower integer. Well, it's the same operation, but you can read this one mathematically and understand it. There's a good chance this is faster, but the extra clock cycle, so if our computers run at 4 gigahertz, which is typical, one clock cycle is 250 picoseconds. Okay, I finally found it. How long is a picosecond? Well, 250 picoseconds is the time it takes light to travel a quarter of an inch. You know how fast light travels? Really fast. So a picosecond is pretty slow. 250 picoseconds is a fourth of an inch. So if you save a fourth of an inch of the speed of light, that's not very much. So this reads much more clearly than this does. In the real world, we don't usually use them to do arithmetic in the sense we think of adding and subtracting. They're used in very specific applications, and we typically use ands and ors and XORs, the bitwise operators, and the shifts. And the only two applications that came to my mind were hardware control and telemetry. There may be others. It's late on a Saturday. I may not have thought of everything, but those are the common ones. So hardware control. So the bits in a word have specific meaning. It's a signal that goes out on a wire and does something out in the physical world. You might be enabling or disabling something. You might be selecting a configuration. You could turn on or off a light or some indicator. But these are not things that most computer scientists are ever going to do. These are things that people who design chips do. This is electronic engineer territory. This is not programming territory. So hardware control is very specific to electrical engineers typically. Of course, my degree is in electrical engineering. These are also used in telemetry. What's telemetry? Well, it's a stream of data that's coming through some sort of a channel. Could be bits over a wire, could be radio signals, could be light signals, all sorts of things. And we're used to pretty wide bandwidth. Bandwidth is the number of ones and zeros you can stuff through your channel in a given amount of time. So your internet connection is typically in the few megabits or megabytes per second. So 100 megabits per second, more or less. And you know, if you're downloading an operating system and you've got 4 gigabytes of data to download, yeah, it takes a while, but you're not that worried about making it efficient. You just wait for the 4 gigabytes to download. But let's suppose you're sending a spacecraft to Pluto, and you need to get information back from that spacecraft. What information do you need? Well, while it's on the flight from here to Pluto, which is going to take, 20 years or something, you want to know how the spacecraft is doing. You know, what temperature is it at, or if the system's operating correctly. And you may want to know if something is on or off. Maybe there's a heater to keep it warm when it gets too cold. You just want to know if the heater is on or off. That only takes 1 bit. And incidentally, when you're talking about this spacecraft going to Pluto, it takes energy to send that information back. And you've got a limited amount of energy because it's powered by solar cells probably, maybe an onboard nuclear reactor, but probably solar cells. And the further away from the sun you get, the less energy there is. So you want to be very conservative about sending information back. If you want to know if the heater's on or off, you only want to take 1 bit for it. In JavaScript, one number takes 64 bits to express. Remember I said most computers today are 64 bits. JavaScript is standardized on that. All their numbers are 64 bits wide. If you want to know if it's on or off, you don't need 64 bits to say that. You can say that with just 1 bit. And I also grabbed, if you have something that has 8 states, maybe you want to know the temperature, and all you really care about is 8 levels of temperature from cold to hot. Well, you only need 3 bits to do that. You don't need 64 bits to communicate that. And so you're going to start packing these bits into a single word. And that's what this looks like. And incidentally, I spent much of my career looking at pictures just like this. believe it or not. So sensor, this is our temperature measure on the spacecraft, right? We can say it's on or off, and each measurement has 8 possible values. So the on-off, which takes 1 bit, and 5 measurements at 3 bits each, can be packed into this 16-bit word. And so instead of taking 1, 2, 3, 4, 5, 6 64-bit words to communicate, which would be what, 384 bits, I can communicate that information in 16 bits, which takes less energy, less time, and that's all very important if you're flying a spaceship out in space. That's easy for me to say. Okay, so I'm going to show you 2 examples. What if you want to set the value into measurement 0? You don't want to disturb any of these other bits, right? If you've already recorded whether the thing's on or off, and I guess if you're going in order, you wouldn't have already recorded measurements 1 through 4, but you don't want to change any of these other values. You just want to change those 3 bits. How are you going to do that? Well, this is where exclusive OR, and shifts come in. So to start off, we want to get 3 bits set here. So we pick a number that's all ones, 3 ones in a row, which happens to be the number 7. And when you're doing bit arithmetic, you tend to talk in hex or binary. A lot of computer programming languages don't accept binary natively. Some do, but they all accept hex, usually with the prefix 0x. That means this is a hexadecimal 7, which is the same as a decimal 7. But when you're masking, you tend to do it in hex anyway. So 3 ones in a row gives me the 3 bits for the width of my measurement 0. But notice the 3 bits are down here at the end of the word. They're not up here, right? So now I've got to shift them left 12 positions. So these 3 bits don't click. Sorry. Boy, I missed all sorts of things. Sorry about that. So these 3 bits now, because I shifted them left 12 spaces, line up with the 3 bits for measurement 0. Okay, you say, how does that help me set it? Well, we're getting there. The first thing we have to do is we have to clear those 3 bits. I'm sorry, I jumped a step. Yes, we're going to need to clear, so we need 3 zeros here, not 3 ones, and that's where you use the exclusive OR. If I exclusive OR with all F's, that's all ones, that means everything that was a 0 will turn into a 1, everything that was a 1 will turn into a 0. So now I've got 3 zeros that line up with measurement 0. Now I can AND my sensor word. Remember, this is my sensor word here. If I AND it with this mask, everything that's a 0 is going to get turned off. So these 3 bits are going to get set to 0. The rest of these bits will be undisturbed because 1 and something gives you something. 1 and something gives you something. It doesn't matter what was in there, it will stay the same. We won't change it. So that's why we AND, is to clear those bits out. Then we get our sensor measurement, whatever it was. Let's suppose it's 001. So we're not at the lowest level, we're 1 step above the level. Now we shift that 001 12 positions to the left. So it started out here, that's what we read, and we shift it so it lines up here, 001, and now we OR to put that into that position. Why do we use OR? Well, these 3 bits are 0, so my 001, I'll have 0 or 0 gives me 0, 0 or 0 gives me 0, 0 or 1 gives me 1. Every place else I have zeros in this word, and so these bits will not be affected by ORing with zeros. They will stay whatever they were. And so to set those 3 bits, we have to go through these steps here. Now you can also see that to set these 3 bits, this code is going to be exactly the same, except the shift count is going to be 9 instead of 12, because we only need to shift over 9 positions to get to here. And so we could express all of these numbers as decimal numbers, but they don't mean much in terms of thinking of the positions of these bits. You do bit manipulations when you care about the positions of these specific bits. And we don't add or subtract, we AND and OR. AND is kind of like subtracting, and OR is kind of like adding, but they're not exactly at all. We use AND, OR, XOR, and shifts to get everything in the position we need. Now suppose we want to read the value of measurement 0. It takes fewer steps. We still have our mask with the 3 bits that are turned on. We shift it over 12 positions so it lines up with measurement 0. And then we AND the sensor word with the mask, and that gives us our measurement 0, because remember, these are all zeros except for 1, so that's going to turn off everything in all of these positions and leave these 3 the same as they were, because whatever was here and 1 will give us whatever was here. If it was 0, 0, 1, we'll have 0 and 1 gives us 0, 0 and 1 gives us 0, 1 and 1 gives us 1. But the 1 is way over here, so now we have to shift it 12 positions so it's down in this location so we can read it as the number 1. And that's called normalizing the answer. Don't worry about why we call it normalizing. So setting the value in there takes a few more steps than reading the value out of there. But you can see, if you're worried about where bits are at in the word, this is why you need AND, OR, and shifts. I would feel pretty confident saying that the vast majority of you will never work with bits at all in your career. You just will never care about them. A very few of you may wander down the same convoluted path that I did, and you may spend 35 years caring about where the ones and zeros are at. But even if you never care, at least now you know why we can do this, all right? So if you've stayed aboard this long, I really appreciate it. Like I say, I will say now, if you have questions, just post a response to this announcement and I'll see if I can answer and clarify things anymore. Thanks so much.